to actually draw a possibility diagram. Okay, and we have learned how there are different ways in drawing our possibility diagrams. Okay, we have the one that has dots in it, otherwise we have the sum and product ones. Okay, using the possibility diagram, we are able to then find out what is the probability for all the events that we need to find. Okay, so I think that from yesterday itself, okay, you already have some sensing in terms of the possibility diagram. So for practice now 4, in your page, in your textbook page 41 and 42, I'll leave it as your own practice. Okay, I shall not go through them. Alright. What we'll do is to look at 3 diagrams. Okay, wait, today got homework due. Okay. So let's look at 3 diagrams now. Okay, so why is it that we have to learn 3 diagrams? The reason is because, okay, there is a limitation to possibility diagrams. We know that in our possibility diagrams, there's always 2 axes. Okay, whereby maybe one axis is the first draw, the other one is the second draw. Otherwise, we can have also a table. Okay, there is a sum or product. Again, first draw, second draw. So there's always at most 2 events, okay, that can happen for us to use a possibility diagram. But what if I want to do more draws? So for example, what if I have a bag of maybe marbles, different colored marbles inside? I take once, okay, it may change the probability. I take another second time, okay, and what if I want to do a third time or even a fourth time? Okay, you notice that if I have to do a third draw or fourth draw, your possibility diagram cannot cater to that kind of scenario anymore. Okay, then therefore we have to learn a 3 diagram, okay, in order to cater to scenarios that are more than 2 events happening. Right? So for example, okay, if let's say I'm trying to flip a coin, okay, that has heads or tail. So the first flip, we have heads and tail, probability half-half. Okay? And then after that, if I want to flip it again, okay, then the combination may differ. First flip, if I have it at tails, second flip can either be heads or tails. Likewise for the first flip to be heads. So again, it is half-half, half-half. Okay, this is the second flip. In the 3 diagram itself, what it can cater to is for us to extend even further to do a third flip. And you notice that when I do a third flip, your 3 diagram can look even messier. Okay, if you like to, of course, we can always extend it, 4th flip, 5th flip, and all that. Okay, so notice that in my 3 diagram, I put the probability on the branches itself. At this juncture that we are starting to learn about 3 diagrams, okay, the probabilities are actually all equal. Later on, as we further our understanding, okay, we will learn how to actually condense it further, maybe talk about this situation, such that the probability may not actually all be equal. Okay? Now, from a 3 diagram itself, we can also observe the different outcomes that it could actually have. So remember from our possibility diagram, okay, if I have a first draw versus a second draw, okay, so let's say maybe I'm drawing cards. Okay, the different dots will actually tell me the different outcomes, the total number of outcomes, right? Yesterday, that was what we learned about possibility diagrams. So having 9 dots will tell me that there are a total of 9 different outcomes. My sample space has a size of 9. Okay, what about from 3 diagrams? How would I know, okay, what are the different outcomes that I can have? Okay, so by following the branches of the 3 diagram, it's called a 3 diagram because it looks like a tree. All these are what we call branches. Okay, so if we follow the track itself, I will be able to see how many different outcomes there can be. So if I want to list out all the possible outcomes in this particular example that I'm giving, you will see that I have the first one over here, which is all heads. Okay, so that is the first outcome. My second possible outcome, okay, is heads and tails, but following that track. I can do the same for all. Till the end, we have tails. And I will see that I have a total of 1, 2, 3, 4, 5, 6, 7, 8. Total of 8 different outcomes. Okay? So that is how we can see the size of the sample space from a tree diagram. Okay? Any questions at this juncture? Okay, so using this tree diagram, let's look at work example 5. Probability of getting 2 heads and 1 tail. Okay? The question says 2 heads and 1 tail. It didn't specify the sequence that it is in. It doesn't have to be HHT. Okay? But HHT is one of the options. Okay? There can be other options as well. We can have maybe HTH. Okay? THH. Right? So these are the different possibilities that we can have. Okay, I don't think we can have any other combination already lah. Okay, so looking at our outcomes over here, maybe let me just write down all the outcomes. So earlier on we said that there's a total of 8 different outcomes. So our denominator will be 8, that's the size of the sample space. Okay, so since we are only looking for 3 favorable outcomes, okay, and it only happened for a total of 3 times, okay, 1 each, so our answer will be 3 over 8. Okay, so to find out the probability from our tree diagram, at this juncture, we are really looking at all the different outcomes and identifying them. Okay. Later on, as we advance our learning and understanding of tree diagram, you will notice that we can simply multiply, okay, or add. Alright, so later on I'll talk more about it when we arrive at that stage. Then in part 2, to find the probability of at least 1 tail, okay, so we think about what are the possible outcomes. Having at least 1, okay, that means that it can be 1, twice, or thrice, as long as it is not none of it. Okay, so if you really want to think about all the different combinations, you could. Okay, so these 3 are when there's only 1 tail. And then we can have it when there's 2 tails. Okay, so 1 tail, 2 tail, and then the last one is where there's 3 tails. Okay, but of course if you want to do this, you find that this is very inefficient, right? Okay, go and think about all the different cases. Okay, if you think about all, then of course if you do it right, you will know that it's 7 over 8. Okay, but if you notice, at least 1 tail has the same idea as, okay, 1 minus probability of no tail. Right? Because at least 1 means that you must have 1, 2, or 3. The complement of it is actually no tail. Alright, so that means you can have 1 minus the probability of no tail. And that would actually be none other than the combination of all heads, which is 1 out of 8. And we can easily find that it is 7 over 8, rather than having to do the tedious counting process. Okay. Any questions at this juncture? Right? If not, let's take a look at practice now 5. When you draw your tree diagram, please draw it neatly rather than cramping all of it up at one corner of your page. Okay, so looking at question 1, right? It says that Imran is a darts player. There is an equal probability that he will hit or miss the bullseye. So the chance is the same. He aims for the bullseye and attempts 3 throws. Okay, so try it 3 times. We want to draw a tree diagram to represent this idea. Okay, so because there are 3 different throws, we need to have 3 separate columns. Okay, and then we are trying to get hits or hit or miss. Okay, so you can use the letter H to represent hit and M to represent miss. Okay, since we're expecting to go up to 3 throws, then your first column you might need to draw it wider. Okay, so that it gets narrower as it progresses. Okay, so hit or miss, then second throw, hit or miss again, third throw, okay, in your usual tree diagram, you need to have a header. So that's why you need to label at the top of each column what is the event that's happening. Okay, sometimes you can use more intuitive labels like maybe blue, green, red, B, G, R. Okay, but then for this hit or miss, maybe you want to have a key, H for hitting, M for missing. Okay, so usually we have a key as well. Okay, since the probabilities are all equal, okay, so in such a tree diagram, if you don't label, we assume that it's all equal. Okay, otherwise you could put in the probability as well. Okay, maximum probability is 1. So since they're equal probabilities, that means half each. Drawn the tree diagram for you already. Could I give you probably about 4 minutes? I want you to answer the remaining 2 parts of the question. Find the probability that he misses the bullseye once and he hits the bullseye at least once. Okay? Give you 4 minutes to go on that. drawn, right, you will find it difficult to identify the different outcomes. Okay, so do try to draw it in a proportionate manner so that you can follow the correct path in the track. Okay, I think most of you are able to get the answer. It's 3/8 and 7/8. Right? Okay, so missing the bullseye once, okay, so you can actually follow and find out when is it that there's only one M, okay, and there are 3 of such occasions. So this is one of them, this is one, and then also this one over here. Okay, so these are the 3 different outcomes by following the path that misses bullseye once. And then hitting bullseye at least once, earlier on mentioned already, you can consider 1 minus, okay, hitting bullseye at least once means that you hit minus 1 minus hitting the bullseye, none of it, okay? So that means probability of this miss. Okay, and then you get 7/8. Right? Let's look at the second question. Okay, for second question, right, you have a tree diagram already partially drawn for you. Okay. However, the reason why I want to point this out is because there is this sum column and product column. So unlike our possibility diagram, okay, whereby we can have a special way of writing it where we account for the sum and the product, when it comes to tree diagram, there isn't such a way to actually present it other than drawing the tree diagram itself and having separate columns to show the sum and the product. Okay? So in question 2, you're told that you're drawing some numbers from different boxes. From box A will be 1, 2, 3, 4. From box B will be 1 and 2. So to continue and complete this tree diagram, you should look as such. And then you proceed with finding out the sum for each path. So in this case, it's 1 plus 1, that's 2. Product is 1 times 1, that's 1. And then you continue to do for the rest, you should be able to get these values. The sum is it? 3 plus 1 is 4. Oh, sorry. Oh, right. Other than that, it's okay, right? Okay. Then, part 2, part A, you want to find the probability of at least 1 is obtained. Okay? So, we're just solely looking at the path itself. Okay, what kind of combination? At least 1, 1, so that means it can be 2 1s or 1, 1 only. Okay, so therefore we're looking at this path. Get a red marker. Okay, this one, this, and this. Right? So there are actually 5 different possibilities. And total of 1, 2, 3, 4, 5, 6, 8. Okay, 5 favorable outcomes out of total of 8 possible outcomes. Okay. complete part B, C, and D on your own as well to find out what is the probability. Alright? Part B, what will your answer be, Vanessa? Where is Vanessa? Yes. Answer for part B. 1/4. Okay, so let's see. We have only one tree over here. So therefore, out of 8 possible outcomes, right? Why is it that it's 1/4? 2/8. So therefore we get 1. Okay. And then part C, to find the product, the probability of the product that is at this 4. Okay, what will your answer actually be? Xu Jian. Answer, part C. Half, why half? Sorry? 4/8, okay? So to be at least 4, we have this one, this one, this one, and this one. Okay? So 4 of the different possibilities that will give us product of at least 4. Okay? And then part D, sum is equal to product. What would that probability be? It is 1/8. Okay, so sum equal to product, we just have to compare the columns and we find that there is this one over here, okay, and nothing else. So therefore we have 1/8. Okay. Questions? Right? Okay, with that, our chapter exercise 2A homework will be question 15, 16, 18, and 20. Okay? It shall be due on next Wednesday, 25th January. Okay? After Chinese New Year. Okay? So far for exercise 1B, I only received 1 piece in my locker. So reminder to please make sure you remember to submit by Friday. Okay. Right. Now let's move on to 2.3. Lord. 950 to understand what are mutually exclusive events. Okay, a large part of our probability understanding, okay, is to understand what are mutually exclusive events, independent events, as well as dependent events. Okay, so we start off with understanding what are mutually exclusive events and what is it that we can deduce, okay, when we have mutually exclusive events. Right? I think I adapted a little from the question in your textbook. So the investigation activity. Okay. So let's take a look at it. We have 8 cards. Okay, number 1 to 8, and then we are defining, okay, 3 different events as such. A to be the one where we draw a prime number, B to be where we draw a multiple of 4, and C where we draw an odd number. Okay. The first question is asking you to list the sample space, so that will be straightforward. We only have 8 cards numbered 1 to 8. Okay, so therefore, sample space would be the set. Okay, from 1 to containing the numbers 1 to 8. Okay. And then for the different events that we have over here, let's think about what are the favorable outcomes for each of the event. So prime number, okay, what are the numbers that fulfill this prime number idea? Okay, so what are the prime numbers? Safe. Where is safe? Yes. What are the prime numbers from 1 to 8? 2, 3, 5, 7, 8. Okay, and then multiple of 4, needless to say, we should know. 4 and 8. And then likewise odd number, your 1, 3, 5, and 7. Okay, so those are your favorable outcomes. So if let's say I want to find out what is the probability of A occurring, that means picking a prime number. That will mean that I have 4 of this that satisfy, that's favorable to this event. So the probability will be 4 out of 8. That is equals to half. Okay. We do the same to find out the respective probability for the events B and C. That will be 2 over 8, 1/4, as well as 4 over 8 again, half. Okay. Now, we notice that between the events A and B, okay, between events A and B, there is no overlap in the favorable outcomes. Okay, so 2, 3, 5, 7 is not found here, 4 and 8 is not found here. Okay, so there's no overlap. Whereas if I were to compare A and C, I noticed that 3, 5, and 7 are common in the 2 sets. Okay, so there is overlap. Okay, so let's take a look at when we have A union B. Okay, so we have just learned our set notation, right? So A union B will mean that it's all these elements together. So 2, 3, 5, 7, and 4 and 8. There's no overlap in the elements at all. Okay, so there's a total of 6 favorable outcomes out of 8. Okay, and that will be simplified to be 3 over 4. Okay, and then if you were to compare probability of A plus probability of B, okay, A we know that it's half, for B is 1/4. It also gives us 3/4. Okay. What if we do something similar to probability of A and C. Okay, for A and C there is an overlap. Okay, so for unique numbers wise, we are looking at 1, 2, 3, 5, 7. Total of 5 favorable outcomes out of 8. Okay, whereas probability of A plus probability of C would actually be half plus half. That's 1. Okay, so what is it that I'm trying to draw over here? Notice that for A union B and A plus B, the probability itself, they are actually equal. But then, okay, for this case itself, for A union C, this 5 over 8 and this is 1. They don't add up to be they don't equal each other. Okay, so when is it that they will be equal and when is it that they will not be equal? Okay, it lies in the fact that whether there's any overlap at all. Okay, in fact, there's a name for it. We call it mutually exclusive. Okay, so mutually exclusive essentially cannot occur at the same time. Okay, for example, alright, can Miss Pang and Mr. Arthur Lee teach at the same time? Teach at the same time. You want Mr. Lee and your form teacher and I teach at the same time? It's possible? I think it's not possible lah, okay? I'm surprised you all say it's possible. To me, it's not possible. So they cannot happen at the same time. So the event of Miss Pang teaching you maths and Mr. Lee teaching you maths, okay, they are mutually exclusive events because they both cannot happen at the same time. You understand? Another example, can you eat lunch and dinner at the same time? Yes. Okay, maybe some of you can okay, because you don't eat lunch at all, your dinner becomes your lunch. Okay, but technically speaking, if you're eating at 12 p.m., that should be called lunch. It should not be called dinner as well. Okay, so that's what we call mutually exclusive events. So, to define mutually exclusive events, they are events that cannot occur at the same time. Okay, so what we see over here is that for events A and B, right? Okay, there is no overlap, right? Which means that these two events itself, getting a prime number or getting a number multiple of 4, they cannot occur at the same time. There is no overlap. They are mutually exclusive events. For mutually exclusive events, we are able to conclude that if I want to find the probability of the union, okay, it will be equals to probability of A plus probability of B. Okay, whereas when there's an overlap, it means that they are not mutually exclusive events. Okay, they are not mutually exclusive. Therefore, we observe that the union itself, okay, is not equals to the addition of the probabilities. Okay. Okay, let's look at how we can apply this. In fact, this idea itself, I'm sure we have already done something similar, just that we never drew that connection to understand mutually exclusive events. Okay, maybe practice now 6, you will be able to actually get the probability without thinking about mutually exclusive events. But when we look at practice now 7, okay, surely we will need to have an understanding about mutually exclusive events. So let's do practice now 6 first to warm ourselves up. Okay. thinking of drawing a 7, I hope you know your playing cards. Are you familiar with your playing cards? Otherwise, Chinese New Year, you can go and play with your relatives. Okay. 52 cards, 4 different suites. Okay, you have your diamonds. It's a suite, right? S-U-I-T-E. Yeah, you have your diamond. S-U-I-T or S-U-I-T-E. I don't remember, okay? It's a suite, right? So, you have your diamond, your hearts, your spades, as well as your clubs. Alright? You all know what I'm talking about? Great, okay? So, this kind of thing, you're very energetic. Okay? So, we know your priorities now. So, 52 play cards, 4 different suites. Each suite got 13 cards. Okay? 13 cards itself, we got the numbers from 1 to 10, and then we have the Jack, Queen, King as well. Okay? So, to draw a 7 itself, how many 7s are there in your entire set? 4, right? So, therefore, 4 out of 52 cards. Make sure you simplify your fraction. Okay, we get 1 over 13. Okay? What about the probability of a picture card? How many picture cards are there? Jokers don't count, okay? 12. Okay, so we have Jack, Queen, King, 4 different suites, so a total of 12 divided by 52. Right, and that will be equals to 4 over 13 when simplified. Okay, so looking at part 3 now, we want to find the probability of drawing either a 7 or a picture card. Okay, so the thing that you draw can either be a 7 or a picture card. Can 7 and picture card happen at the same time? Cannot, okay, it cannot, because 7 is a number, picture card is your Jack, Queen, King only. So therefore, these two events are actually mutually exclusive. So what you could consider, you can consider it as 7, probability of 7 or plus probability of picture card. That will be equals to 1 over 13 plus 4 over 13, simplifies to 5 over 13. Okay, yes. 3 out of what? 13. Okay, count for me. 12. Sorry, my bad calculation. Sometimes I do until very late, so my head and eyes are not connected. Okay? So any questions at this point? Okay, of course, right? Other than recognizing that they are mutually exclusive events, which naturally sometimes we don't think in that manner, because honestly, I sometimes don't think it's mutually exclusive events or not. I just have to go and count, right? Okay? What is the chance of getting a 7 or a picture card? I just count how many 7s are there, and there are 4. Picture card, I have actually total of 12. So alternatively, what you can do is that you have 4 plus 12 divided by 52. It will also simplify to be 4 over 13. That's another way of solving as well. Okay? I'm not limiting you or trying to force you to think about mutually exclusive events over here. Okay, you can go and do your basic counting, which we already did when we were in Sec 2. Okay? Probability of neither a 7 nor a picture card. That means you don't want any of this. It is actually the complement of your answer in part 3. over 13. Right? So let me just correct my answers on my before I forget. Questions so far? Right, so we understood how mutually exclusive events can work. Let's continue with part 5 and part 6. So part 5, we want probability of getting a diamond. Okay, how many diamonds are there in a set of cards? How many? Suddenly don't know. How many diamonds are there in a deck of cards? 4. Diamonds there. We have 13, okay? Because got 4 different suites, right? We have your diamond, hearts, clubs, and spades. Each one got 13. So to get a diamond, it is 13 cards out of 52. That is 1/4. Right? Okay? Diamond what color? Diamond is what color? Black, red, okay? So, last one. Can say either of the 7 or a diamond. Can 7 and diamond happen at the same time? Yes. Okay, so are they mutually exclusive? No. Okay, they are not mutually exclusive. So you cannot just take probability of 7 plus the probability of diamond and add them up together. Okay, so what you have to do is to literally go and count, okay, what the probability is. So, probability of 7 or diamond, okay, that could either be the 3 sevens that are not diamonds, okay, so that means the ones from your hearts, okay, spade and club, so 3 of them. And then the rest of it, your diamonds, you have 13 cards in total, including the one that is both 7 and diamond. Okay, so you have to go and count the favorable outcomes. Alright, so there's a total of 16 cards that fulfill this event. Therefore, okay, that simplifies to 4 over 13. Okay. Okay, now let's look at practice now 7. This is the part where we might need to think a bit. Okay, let's start with something simple first. Okay, looking at practice now 7. That's in your textbook, page 53. Okay, so there are 4 teams. Okay, PQRS vying for the National Volleyball Championship. Any volleyball girls in our class? Tomorrow going, right? Oh, then correct. Tomorrow is the first match, right? Just now Mr. Paul got say. Okay. So I hope your probability of winning is 1. Okay, rather than these miserable numbers. Okay. So let's look at part 2 first, alright? Rather than jumping into part I. Okay. So part 2, we want to calculate the probability that either P or Q wins. Okay. Now what do you think that will actually be? Can they both happen at the same time? No, right? Okay, so therefore they are mutually exclusive event. If P win, Q cannot win. If Q win, P cannot win. So confirm is mutually exclusive. Okay, so therefore I can simply add up the corresponding probabilities. That will be 1/5 plus 1/6. And that is equals to 11/30. Right? Now part B. Probability of either Q, R or S wins. What do you think the probability would be? Let's see. Yue Yi. Where is Yue Yi? Yes. What do you think the probability is for either Q, R or S wins? And tell me the working, the process. What will you do? Okay, we take 1/6 plus 1/7 plus 1/8. That means it is the probability of Q winning, R winning, and S winning. Why is it that we can do that? Can you explain to us why is it that you can do that? Because what? Just because numbers are there, they can add them up already. But there must be a condition in place, right? Sorry, because it says either or. Okay, that is not the key point over here. The key thing is that you need to realize in this situation, okay, in this particular context, the events, okay, of Q, R, S, or even P winning, they are all mutually exclusive events. Okay, so long if there's an overlap. So let's say, okay, you getting A1s, alright, for your maths exam. Is it a mutually exclusive event? For example, okay, Yue Yi getting A1 for maths, okay, versus Matthew getting A1 for maths. Are these two events mutually exclusive? Are these events mutually exclusive? So that means if they are mutually exclusive, what does it mean? It means that if Matthew get A1, Yue Yi cannot get A1. Okay? Is that going to be true? No, okay? It better not be, okay? So, so that means that, okay, these two events are not mutually exclusive, okay? There is an overlap, there's a possibility of overlap, right? So, but then in this particular case, when it comes to winning a volleyball competition, there can only be one winner. Okay, so they are definitely all going to be mutually exclusive. That's why we can add up the probabilities of winning together like that. Okay, and that in this case will be 73 over 168. Okay. Now next, part C. What is the probability of Q does not win? Okay, I want you to think about this. What would the probability of Q does not win actually be? Josh. What is the probability of Q does not win? Sorry? 5 out of 6. Why do you get 5 out of 6? Okay, 1 minus 5 out of 6. But why? Why isn't it the case whereby I just take 1 over 5 plus 1 over 7 plus 1 over 8? Why is it that this one must be the answer? Why not 1 over 5 plus 1 over 7 plus 1 over 8? Sorry? 8? Sorry. Jumble up my numbers, thank you. It is what George said, right? Okay. So my question now is, why is it that it is 5 over 6? Why is it that this is the answer? Why not 1 over 5 plus 1 over 7 plus 1 over 8? Sorry? Why are we bringing in the idea of independent now? I think we're not talking about independent events now. Okay? What does 1 over 5 plus 1 over 7 plus 1 over 8 even mean? What does it mean? Any guesses? Before I choose my sticks? Gladys? Where's Gladys? Why that kind of sound effect? Yes, Gladys, can you tell me what does 1 over 5 plus 1 over 7 plus 1 over 8 mean? Probability of P, R, or S winning. Okay, so this is actually probability of P or R or S wins. Right? Isn't it right to say that if Q never wins, means P, R, or S wins? No, man?
Correct.
Q does not win, that means P, R, or S wins what? Is it correct?
Yes.
But then what is the answer over here?
I don't know.
You're going best calculator. I also don't know what's the value.
Hey, who's saying you can calculator?
It's 131 over 280, right? Okay, so why is it that these answers are different? Why? It's more than 4. There's more than 4 teams. How do you know there are more than 4 teams? So Carrie says there are more than 4 teams. Other than P, Q, R, or S, there's actually more than 4. How do you know? Sorry? Part 1, okay, because of your part 1 question. Okay, so we're trying to answer part 1 question concurrently. If you notice the probabilities over here, right? 1 over 5 plus 1, 6 plus 1, 7 plus 1, 8, they don't add up to be equals to 1. Okay? So what does this actually tell us? Alright, this will actually tell us that there will actually be more than one team itself. Okay? Because if it's strictly just these 4 teams and they are all mutually exclusive events, okay, strictly speaking, they should all add up to be 1. Okay? If they are actually 4 teams in total. But in this case, because it's not equals to 1, therefore, I cannot start to think about Q does not win, means that P, R, or S wins. Okay? These 2 events are not equal, okay, simply because there are actually more teams in this particular question. Alright? If it's just these 4 teams only, then of course, the 2 values should strictly speaking be equal. Okay? So, let me just write the answer for part I on the whiteboard as well. Okay. This is the question. that that understanding, okay, that realization that in this context, the events are actually mutually exclusive. We need to have that understanding first, so we must state that out. Okay? Then, what we're expecting, since they are mutually exclusive, is that we expect that the sum of the probabilities to be equals to 1. But in this particular case, it is not equals to 1. Okay? Therefore, we say that there are more than 4 teams in the competition. Okay? Alright? Now, okay, what if I tweak this question? Okay, this question suddenly came into my mind. Alright, so I want you to follow what I'm trying to think and try to say here. Okay, what if I calculate, okay, the given probability? So I'm just going to start writing it short now. Okay, all this means that these teams are winning. What if my probability ends up to be more than 1? What does this tell us? What can this tell us about the nature of this competition? It's rigged. Do you have something more mathematical? If the probability of all these teams winning, okay, adds up to be more than 1, what does this tell us about this competition itself? That what? That more than 1 team can win, yes, okay? That these events are not mutually exclusive. Okay, that means that in this competition itself, we can have maybe P and Q winning. Okay, they can be co-winners maybe, alright, or R and S winning. Okay, so there's that overlap. Okay, because when there's an overlap, then the probability, okay, would likely, alright, be more, the add up, okay, will actually be more than 1 itself. Okay, so that's something that we can tell from this question and further our understanding about mutually exclusive events. Okay. Right? So going back, okay, to part D. Okay, part 2, part D. Let's finish up this question, then we call it a day already. I mean, your lesson end time is coming already soon. Okay, I don't know whether is it a good thing that you are doing or a bad thing. Don't know how should I feel about this. Alright, part D. Okay, probability of Q, R, and S do not win. Okay. Personally, I hate it when it is always do not something, makes me think, okay? I'm not sure about how you feel about all this kind of negative compliment kind of idea, okay? So let's try to break down what this actually wants us to do. Them not winning means that, okay, it is the same as saying probability of Q losers, R losers, okay, and NS losers. Okay, I don't like the idea of do not win, so I rather just think about it as losing. Okay, there's a reason why we use such a word, right? Okay, it's not that negative. So probability of Q losers, R losers, and S losers. Is losing a mutually exclusive event? Yes or no? Who says that losing is a mutually exclusive event? Who says it's not a mutually exclusive event? Okay, so losing is not a mutually exclusive event because they can happen at the same time. Okay? Okay, so they can happen at the same time. So what this means is that, okay, does this mean that from this context, P is the one that's winning? No, right? Okay, because we already understood, we have the consensus that in this particular competition, there are actually more than 4 teams. So I cannot say that this is actually equals to 1 minus probability of P, or rather, this is the same as probability of P winning. Okay, I cannot say that. Yes. Your question? Oh no, you're just dancing. Okay. So they are not equal. Okay. So what we got to do, alright, is to think of the complement. Okay. Think about it as 1 minus probability of Q winning, R winning, as well as S winning. Okay, so the complement of losing is winning. What we learned in set, okay, losing is winning, complement of it. Complement of N becomes all, right? Okay, union become intercept become union, right? So 1 minus Q win, R win, or S win. Okay, that is actually your answer over here in part B. Okay, and that will actually be 95 over 160. Okay. Right? So with that, right, okay, when we have addressed that Q lose, R lose, and S lose is not mutually exclusive event, it actually gives us the answer for part 3 as well already. Okay? Where can I erase? Can I erase this already? Yes, huh? Okay, so part 3, our final question for the day. It's correct, right? Sekali I see wrong time. 12:40, yes. Okay, explain why these are not equal. We already said it is because the idea of losing, okay, it is actually not mutually exclusive event. So we explain that. Okay, if you want to, you can end the answer over here already, explaining why. But in case, okay, 10 weeks down the road, you don't remember what does mutually exclusive events mean already, maybe you want to just write an example, okay, when R loses or when Q loses, okay, R could also be winning, or okay, when the event of Q not winning occur, R not winning, R could also be losing. Hence, these events can occur at the same time. Okay? Therefore, we cannot add up the probabilities. Okay? And then we are done with chapter 2.3, and at the end of chapter 2.3, we have a homework. Okay? Exercise 2B, question 6, 7, 8. As much as you're complaining about your homework, okay, tomorrow your home-based learning, I also have to mark your homework, okay? So, it's not that it's a break for either one of us. Okay, when can this exercise 2B be due? Wednesday. Shall we put it together in one full step? Yes, okay. Because the other time, when people say I waste too much full step. Oh. Okay, just do it in the same full step, Unless you really want to waste full step, then go ahead. I'm not stopping you. Okay, so due on Wednesday. Now for tomorrow, home-based learning. Okay, what am I going to assign you? I will be assigning you to cover chapter 2.4 on multiplication law of probability. Okay, there are some videos for you to watch. Some of the videos are made by me, some are not. Okay, so I hope that I deliver whatever that I hope to deliver through the videos. I only will want you to cover up to the idea of independent events. Okay, so when we come back, we clarify any of the problems that you may have, things that you're unsure. Okay, then after we move into dependent events. Alright, so that will be the objective of tomorrow's home-based learning. Okay. By the way, it's an SLS lesson. Okay, so check out your SLS. I will post the detailed instruction on Google Classroom. That will